guys. In this video I'll explain you about the ALU HDL along with the architecture, such as the logic gates, and how everything connects to each other in the ALU. So think of this as a additional resource video for our class. So um, I'll try to keep this video short and resourceful so that you guys can benefit from it. So without further ado, let's get started. So the ALU, if we look at the architecture, if we look at the abstraction, this is what the ALU looks like. We have the two 16-bit inputs coming from the left. So they're X and Y. So X are 16-bit inputs and Y are also 16-bit inputs. Now we also have other inputs coming from the top. They're basically selection. They're selection bits. So they're one bit selection. Basically these inputs are only one bit. So there's ZX, NX, ZY, NY, F, and NO. These are only one bit. Now as for the outputs, the main output it produces is a 16-bit output, whereas we also have two more output that comes out. Now these outputs are only one bit, same as the one from the top. Z OR and NG is only one bit each. Okay, so this is basically the abstraction, so we can't really see any logic gates or any anything that's happening inside the ALU, or what makes the ALU the architecture. So let's get into details about how what makes up the ALU. Okay, so first of all, you might have seen this in class. So in class we've got the ALU Truth Table. So this is basically the we've got ZX, we've got NX, ZY, NY, F, NO, and and the output. So these are the ones that basically they're bits that determine the result of the ALU. So you guys were given tasks to practice these problems by using this table. But the thing is, have you guys ever wondered how ZX, NX, ZY, NY, F, and NO, how did they come from, and how instead of looking at this extracted view of the ALU, how are things working inside the ALU? How are these bits? How are they managing the result? So first, let's before we go into the details, let's look at the API. So we've got the chip, the ALU, and this is the inputs. So like I've mentioned before, we've got the 16-bit inputs, two 16-bit inputs. So they've got X and Y, and we've got these individual 1-bit inputs that are selection bits, so ZX, NX, and so on. We've also got the output, so one output, that the main output that is 16-bit output, and we've got 1-bit outputs, Z, OR, and NG. So basically Z, OR, if the output is equal to 0, like if the output of the ALU, so you see this output right here, if the 16-bit output, the main output, is like all the bits, because there's 16 bits, right? So if all the bits are 0, then Z OR will be true. So see, it says 1 if the output equals to 0. So and if it's not, then it's 0, which basically this means saying that if the output is 0, if the output here 16-bit output is 0, then Z OR will be true. Otherwise, it's false. Same thing for NG. If the output is less than 0, So if it's a negative number, then that means ng will be true, and then otherwise it will be false. Okay, so let's move on to the first HDL code, first part of the HDL code. So the reason why I divided it up is because I want to show you guys how each individual, so you see here there's ZX, NX, ZY and all that. So I'm trying to show you each individual one so that you guys can understand better. So first up, we'll look at ZX first. So I'm just going to annotate the pen. So first we're going to look at ZX and NX, how these two are actually how they are coded, and how the chips and the logic gate works. So ZX and NX. So this part here, so remember, ZX, what does it do? Basically, it says here, if ZX is true, then X, we set X to 0. And NX is, so if NX is true, if the selection bit comes out as true, so if it basically goes in, sorry, not comes out, goes in. If it goes in true, then we negate X. So how it works, if we look at the gates first, so we have the multiplexer here. Now, why do we have the multiplexer? Is because the multiplexer chooses which one to output. So remember, we've got the input here, the 16-bit input. We've got the x is equals 0. So basically saying that if ZX is true, then we set X to 0. So we put 0 here. So that means if ZX is true, then the result would be 0. And otherwise, we would just keep the initial input. We would just use that and output it back. So the output from the multiplexer, the first multiplexer, we name that as X1. Okay, so X1 is the output from the first multiplexer. Now, that is basically the answer to the first here, the first column over here. So the first column is ZX. Now we move on to the second one, which is NX. NX is basically for negating X. So to negate X, we need a what? We need a NOT gate over here. That's why we have a NOT gate. So again, we will use the multiplexer because remember, this is like a choice. It's like a selection. So we need to select which one to output, yeah, and the bit that determines the selection is the NX, and same for here. The bit that determines the selection for this multiplexer is ZX, and as for this one, it's NX. So the output X1 over here will travel down here and then divide into two. So this one goes into the NOT gate, whereas this one goes straight into the multiplexer. So this one basically saying that doesn't do anything. It just goes straight into the multiplexer for the decision making, and whereas this one goes into the NOT gate to negate it first before going to the multiplexer. Now, whatever comes out here is determined by the NX. So if NX is true, then we negate X1. So we basically take the answer from this whatever comes out of this NOT gate. And if it's not true, if NX is not true, then we just use the same answer. So straight from X1, we just keep that answer. We don't do anything. Okay, so the answer from the second multiplexer is X2. That's what we name it. So this is X2, the result from the second multiplexer. So same here so now that we've basically covered ZX and NX, now we just move on to the third, which is ZY and NY. Now they're basically the same thing. We just have to change the the variables. So instead of x, we just have to change it to y. So they're basically the same thing, and as you can see here, just to prove it, because remember I've already explained you here how it works. So this is the same thing. Now I'm just going to prove it by looking by referencing with the HDL code. So here we've got the first Mach16, the first multiplexer. Now the first multiplexer, we've got um, the input. So this is y, yeah, y, the 16-bit input. So it goes into the multiplexer along with the selection bit over here. So this is the selection bit, and then so y equals 0 basically is saying that if zx is true, if zy is true, then we set y to 0. So that's why we put y equals 0, and then whatever comes out is equal to y1. Yeah, we name it as y1. So that's the result from the first multiplexer. And then again, it happens through the same process that I've explained in the previous slide. This one goes into the NOT gate, whereas this one goes straight into the multiplexer. This one goes to the NOT gate and then straight into the multiplexer. And the second multiplexer obviously outputs y2, and the result will be determined by this single bit over here, ny. Okay, now we've covered these four. Let's go into f. Now f, so if you read here, if f is true, then the output will equal to x plus y. And otherwise, if f is false, then we AND it together, so x and y. So we use an AND gate. Now, sorry I skipped it a little bit, but before we go into the f, as you can see here, so now you finish x, zx and nx, right? So these two, that's 1, and that is 2, yeah? So we can say that these two can be converted into this abstracted view over here. So instead of having this x and this is y, instead of having these like these layers of logic gates, we can convert that into this abstracted view, so that we can focus on more a bigger picture in the next few slides. So this is the abstracted view. Okay, so let's move on. So now as I've talking about the part f, so again, this is x plus y or x and y. So that's basically the function for f. So this is why we have, so this is, remember, this is the output from x2, yeah? So if you look back here, the output from here will be x2, whereas this one will be y2. So these basically goes into the f multiplexer. Now before it goes in there, it must go into an AND gate, because remember, our function is AND or plus. So we must also have an add over here. So we have to add x and y. So x goes into the add, and y also goes into the add. Same thing for AND, y goes in here and x goes in there. Now both of them goes into the multiplexer, and then the result will be either one of them. So it can be the AND or it can be the add. So it can be either one of them, and the bit that determines which one it outputs is the F. So this is the selection bit that determines which one will come out. Now, so this is the view that so if you look here, so this is the view. We can convert that into a more abstract view. So we're just going to draw a box, a rectangle, and then we're just going to name that as F. And this is, remember, this is from the last slide. We can scribble that out, and we can have this as the abstracted view. Now that you've got this part right here and this part right here, we can convert those two, and we can add them to this view. So basically, what we're doing here is we're connecting the F with the previous picture. So now we've got F here, and then obviously this is the final picture. Okay, so if we look back at the table, we've done F. Now we're on to the last one, which is NO. So NO, obviously, again, it's just negating the result. So whatever comes out of the F, so remember, this is F right here. If we look back at the slide, this is F. So whatever comes out of there, the result, will be negated using a NOT gate. Or otherwise, if it's not, if NO is false, then we just have to we don't do anything, we just have to take that result and then outputs it. So again, we're going to use a multiplexer for the selection, and the output is a 16-bit output, whereas the NG is a 1-bit output, which is the number 15-bit, and ZOR will be divided into two. So if you look here, the output will be from 0 to 7, so bit 0 to 7, and also from 8 to 15. Now I'll move on to the next slide to explain more about the NG and ZOR, but for now, this part here is called part no. So that is part no, and now let's move on to the outputs for NG and ZOR. Now, the output for NG and ZOR, so NG, like I've told you, NG is a single bit output, so it produces one single bit. So remember, this output here is 16-bit. NG is 1-bit output, and ZOR will produce the bits from 0 to here, if you look back here, from 0 to 7, and from 8 to 15. So we must convert them to 1-bit output too. So remember, in the end we want 1 bit for each. So to do that, we must have, because first of all, we must have NG here. We must put them into an AND gate. With true, so true is 1. So we must put them into an AND gate, and then the output will be NG. Whereas ZOR will be divided into two. One is the 8 OR way. So the 8 OR way, the OR 8 way, sorry, the OR 8 way will, because remember, OR 8 way means each one has 8 bits. So each OR each gate has 8 bits. So after whatever comes out of the OR 8 way will come out as a single bit each. So each of the gates will come out, will produce one single bit. Now in the end we want 1 bit only. So now we've got 2 bits. So what do? We put another OR gate. So that will go into one OR gate. Sorry, my drawing is a bit sketchy, but hopefully you can understand. So these 2 bits will go into one OR gate, and obviously an OR gate will only produce one bit output. So this will come out as 1 bit, and then we'll go into a NOT gate and produces C OR. If you check with the Hdl code, it should be the same. So the OR 8 way basically produces one output here, and then those 2 outputs will OR together in an OR gate, and then will produce one single bit output, and then goes into the NOT gate to negate it, and then that will produce Z OR. So we've got NG over here, and we've got Z OR over here. Okay, yep, that is it. So this is basically the total. Basically, when you add up all the parts together, you would get this big picture over here. So this big picture is basically the logic gates and whatever is happening inside the ALU. That basically connects with the truth table, and also connects with the Hdl code that you see here. So these are the chips and gates that you will that you will have to understand, so that you can get a better understanding of how the ALU works. So in the later lessons in this unit, you won't basically focus much on how the insides of the ALU work. There will be a lot of abstraction happening, so you will mostly see you will mostly see this picture right here, or this diagram. So this diagram is basically the abstraction of this entire diagram here. So you won't have to worry about what's happening inside the ALU. So all you have to focus on is just the inputs and outputs and all that, because the ALU will play a big process in understanding the hex CPU, and basically the topics covered in later units, and later in the unit. So as for now, hopefully you can understand how the ALU works and how the abstraction covers up all the logic gates that's happening inside the ALU. So if you understand the logic gates, what's happening inside it, then you will understand how it works, and you'll get a better understanding of it. Yep. So this is it for this video. Hopefully you can benefit from it, and yep. Good luck.